There is a planet hurtling through the darkness between stars right now, not orbiting a sun, not warmed by any light, completely and utterly alone in the infinite cold of interstellar space. It has been traveling for millions of years, possibly hundreds of millions of years. It will travel for millions more, perhaps billions, perhaps until the end of time itself. Picture this world in your mind. Its surface temperature sits at approximately 30 Kelvin. That's negative 243 degrees Celsius, negative 405 degrees Fahrenheit. To put that in perspective, that's just 30 degrees above absolute zero, the coldest temperature theoretically possible in our universe. The coldest temperature ever recorded in a laboratory on Earth is about 0.0000000001 Kelvin, achieved using elaborate laser cooling techniques. This planet exists naturally at 30 Kelvin, a temperature so extreme it defies everyday comprehension. At this temperature, bizarre physical phenomena occur. If you could somehow transplant Earth's atmosphere to this frozen world, the nitrogen that makes up 78% of our air would freeze solid almost instantly and fall as pale blue snow, accumulating in drifts kilometers deep. The oxygen we breathe would condense into a strange metallic blue liquid, pooling in ancient impact craters like lakes of liquid sapphire, its surface perfectly still in the absolute absence of wind or weather. Carbon dioxide, the gas we exhale with every breath, the gas that makes soda fizzy, would form mountains of dry ice kilometers high, their frozen peaks catching the faint starlight in eerie, ghostly reflections that no one will ever see. This planet is roughly the size of Earth. Beneath its frozen surface, there might be mountains carved eons ago by tectonic forces that have long since frozen into eternal stillness. There might be canyons vast and deep, valleys that once knew flowing water or lava, the scars of ancient meteor impacts that struck billions of years ago when the planet still orbited a star. The planet might have an atmosphere, perhaps 100 times thicker than Earth's, composed primarily of hydrogen and helium, the lightest elements, captured from the protoplanetary nebula during the planet's formation, plus heavier gases like nitrogen and carbon dioxide that outgassed from volcanic eruptions in its ancient past. Deep beneath its frozen surface, insulated by kilometers upon kilometers of ice acting as a thermal blanket, there might even be liquid water. Water heated not by any external sun, but the slow, patient, inexorable decay of radioactive elements buried deep in the planet's rocky core. Uranium-238 with a half-life of 4.5 billion years, thorium-232 with a half-life of 14 billion years, potassium-40 with a half-life of 1.25 billion years. These elements have been releasing heat steadily since the planet formed, and they will continue to do so for billions of years more, providing a feeble but persistent warmth in the planet's deep interior. And this planet, this frozen, lonely wanderer, is not alone in its exile. Recent discoveries published in the most prestigious scientific journals suggest there may be billions, perhaps even trillions of these rogue planets drifting through our Milky Way galaxy at this very moment. Worlds cast adrift from their parent stars through violent gravitational interactions during the chaotic early phases of planetary system formation. Worlds now wandering the cosmic void in perpetual darkness, sentenced to an eternity of cold isolation. Planets where the sun never rises and never sets, because there is no sun. Planets where day and night have no meaning, where the concept of seasons is absurd, where the temperature hovers just barely above absolute zero, unchanging across eons, where the only illumination comes from the faint, distant glow of stars so far away they provide less light than a full moon provides to Earth on a clear night, barely enough light to cast the faintest of shadows. Now imagine, if you will, standing on the surface of such a world. You would need a highly advanced spacesuit, of course. The cold alone would kill any unprotected human in less than a second, freezing the water in your cells instantly, stopping your heart mid-beat, turning your body into a frozen statue. The suit would need active heating systems running continuously just to keep you alive. Your breath would freeze inside your helmet if the recycling system failed for even a moment. Above you stretches a sky unlike anything you've ever seen or could see from Earth. No sun warming your face with its familiar golden light, no moon tracking its ancient path across the heavens, waxing and waning through its monthly cycle, no nearby stellar companion to mark the passage of days, weeks, months, or years. Just the endless, infinite tapestry of stars, unblinking and unchanging, so distant that even the brightest among them appear as mere pinpricks of light against the absolute blackness of space. But what a view it would be! The Milky Way would stretch across the sky in stunning, breathtaking detail, a river of light containing hundreds of billions of stars, completely unpolluted by any nearby stellar glare. From Earth, we see the Milky Way as a faint band in the sky, washed out by light pollution and the glow of our own sun. From a rogue planet, you would see it in its full glory, every spiral arm visible in exquisite detail, star clusters scattered like jewels, dark nebulae silhouetted against the background glow. It would be the most spectacular astronomical view in the galaxy, and also the most lonely, the most isolating, the most profoundly alien. Beneath your boots, you would stand on a world that once orbited a star, a world that once knew warmth, heat, the life-giving radiation of a sun, a world that experienced the cycle of day and night as it rotated on its axis, its surface warming and cooling in a predictable rhythm. A world that might have known seasons if its axial tilt was right, experiencing the gentle variation of summer and winter as it orbited its parent star. A world that felt the gentle gravitational tug of sibling planets, perhaps a Jupiter-like giant in an outer orbit, perhaps rocky terrestrial worlds closer to the star, a family of worlds bound together by gravity and common origin. A world that might have harbored vast oceans of liquid water under a thick atmosphere, their surfaces stirred by winds and weather. A world that might have seen the first stirrings of life, simple organic molecules assembling themselves into something more complex, more organized, more alive. Perhaps nothing more than bacteria, perhaps more. Complex multicellular organisms, ecosystems, the beginning of an evolutionary journey that could, given enough time, lead to intelligence.
Then something happened, something violent, something catastrophic, something that changed everything in an instant of cosmic time. A gravitational catastrophe, a cosmic game of billiards played with planets instead of balls. Perhaps this world passed too close to a larger sibling planet, a gas giant whose enormous mass created tidal forces that stretched and compressed the rocky planet, heating its interior, making its orbit increasingly eccentric and unstable. Perhaps the star system's architecture was inherently unstable from the beginning, with too many planets in orbits too close together, making eventual chaos inevitable. Perhaps a neighboring star passed through the system during a close approach in the crowded stellar nursery where the planets formed, its gravity disrupting everything, scattering planets like leaves in a hurricane. Whatever the specific cause, the result was the same. This world was thrown into the void, accelerated to escape velocity by a gravitational slingshot effect, flung away from its parent star like a stone from a sling. Sentenced to wander the galaxy in darkness and cold for billions of years, perhaps until the heat death of the universe itself, when even the stars burn out and everything grows cold and still. What happened to these planets? How many exist out there in the vast empty spaces between stars, invisible in the darkness? Could they actually support life in their frozen depths, powered not by sunlight but by the feeble warmth of their own slowly dying cores? Could microorganisms exist in subsurface oceans, feeding on chemical energy from hydrothermal vents, living in eternal darkness, completely unaware that stars even exist, that the universe extends beyond their frozen ocean ceiling? Could entire ecosystems persist on these wandering worlds? Could evolution continue over billions of years in isolation? Could intelligence emerge in such an environment? Civilizations that develop science and technology without ever seeing the stars, without ever knowing they live on a planet traveling through space? And most disturbing, most unsettling of all, could one of these dark wanderers be heading toward our solar system right now, invisible in the darkness, a gravitational intruder whose passage through our planetary system could scatter our planets like marbles, disrupting Earth's orbit, ending life not through collision but through gravitational chaos, making our world uninhabitable by moving it too close to the sun or too far away? These are not merely theoretical questions posed by philosophers pondering the strange corners of possibility space. These are not abstract thought experiments disconnected from reality. In the last decade and a half, astronomers using some of the most sophisticated telescopes and detection techniques ever developed have begun detecting these dark wanderers. They've found them using gravitational microlensing. They've imaged young ones directly in infrared light. They've analyzed their statistics and extrapolated to the entire galaxy. What they've found suggests we've drastically, fundamentally, completely underestimated how common planets truly are in our universe, and how violent, how chaotic, how ultimately hostile the process of planetary system formation can be to worlds that had the cosmic misfortune of being born in the wrong place at the wrong time, in a system destined for gravitational chaos. The implications are staggering, almost incomprehensible in their scope. If rogue planets outnumber stars, and current evidence suggests they do, by a factor of at least 2 to 1, possibly much more when you include smaller worlds, then the majority of planets in our universe exist in a state we never anticipated when we started searching for exoplanets orbiting other stars. The cosmos isn't filled primarily with orderly solar systems like ours, where planets orbit their star in neat, stable, predictable paths for billions of years, where the architecture of the system remains essentially unchanged from formation to the star's death. Instead, it's filled with orphans, outcasts, exiles, wanderers drifting through the dark on journeys that began millions or billions of years ago and will continue until time itself ends. Refugees from gravitational catastrophes, close encounters, orbital instabilities, stellar flybys, supernovae that occurred in the violent early days of their home systems. And somewhere out there, drifting through the empty space between our Sun and Alpha Centauri, between our spiral arm of the Milky Way and the next, between our galaxy and the Andromeda Galaxy 2.5 million light-years away, there might be worlds that once knew life, worlds that still know life, hidden beneath kilometers of frozen ice. Worlds where organisms evolved in darkness and cold, adapted to conditions we can't barely imagine, thriving in environments that seem utterly hostile to biology. Worlds where civilizations might have risen and fallen over millions of years without ever knowing the warmth of a star, without ever developing astronomy because there was no visible sky to study, without ever realizing they lived on a planet traveling through a vast universe filled with hundreds of billions of galaxies. Today, we journey through evidence that challenges everything we thought we knew about planetary formation, orbital stability, the definition of what a planet even is, and the possibility of life existing in the cosmos in forms and places we never expected. We'll explore the groundbreaking discoveries that have forced astronomers to completely reconsider what a planetary system even means. We'll examine the mathematics of cosmic exile, the cold, unforgiving equations of orbital dynamics that govern when planets remain bound to their stars versus when they achieve escape velocity and flee into the void.
We'll look at computer simulations that replay the violent early history of planetary systems thousands of times with slightly different initial conditions, watching worlds form, migrate, collide, and scatter in an endless variety of outcomes. We'll confront the possibility, increasingly supported by observational data and theoretical models, that we live in a galaxy where the majority of worlds never see their sun, where most planets exist in eternal darkness. Prepare yourselves. We begin.
To understand the significance of discovering rogue planets, we need to understand what astronomers thought planetary systems looked like before 2011. For most of the 20th century, our only example of a planetary system was our own solar system, and what we saw looked orderly, stable, almost clockwork-like in its precision. 8 planets, 9 including Pluto until 2006, orbiting the Sun in nearly circular paths. The planets spaced out in a roughly regular pattern described by the Titius-Bode law, a mathematical relationship suggesting a hidden order in planetary spacing. Rocky terrestrial planets close to the Sun, gas giants farther out, everything in its place, stable for billions of years. Astronomers in the mid-20th century developed theories of planetary formation based on this observed order. The nebular hypothesis, first proposed by Kant and Laplace in the 18th century and refined by modern astronomy, suggested that planets form from a disk of gas and dust around a young star. Material in this disk gradually coalesces through collisions and gravitational attraction, building up planets that settle into stable orbits where they formed. This formation-in-place model suggested planets should remain more or less where they formed for their entire existence. Jupiter formed at 5 AU from the Sun, and 4.6 billion years later, it's still at 5 AU. Earth formed at 1 AU and has stayed there ever since, stable, predictable, orderly. The discovery of the first exoplanets in the 1990s began to challenge this picture. In 1995, Michel Mayor and Didier Queloz announced the detection of 51 Pegasi b, a Jupiter-mass planet orbiting a Sun-like star every 4.2 days. This was shocking. A Jupiter-mass planet couldn't form that close to its star. It was too hot, too close. There wasn't enough material in the protoplanetary disk at that distance. The planet must have formed farther out and migrated inward. Planetary migration. The concept was unsettling to astronomers accustomed to thinking of planetary systems as static, stable configurations. If planets could move, what else could happen? Could they be ejected entirely? Computer simulations in the late 1990s and early 2000s began exploring planetary system dynamics in detail. Researchers discovered that multi-planet systems often undergo violent instabilities. Close encounters between planets could lead to collisions, ejections, or dramatic orbital changes. The orderly solar system we observe might be the exception, not the rule, a survivor of early chaos, now stabilized, the troublemakers long since ejected or destroyed. But this was all theoretical. Simulations suggested rogue planets might exist, but detecting them seemed nearly impossible. They emit no light, they're too small to detect gravitationally except in special circumstances. How would we ever find them? The answer came from an unexpected technique: gravitational microlensing.
In 2011, Takahiro Sumi of Osaka University and his international team of collaborators published a paper in Nature with a deceptively simple title: Unbound or Distant Planetary Mass Population Detected by Gravitational Microlensing. Hidden in that title was a revolution. The team had spent years conducting the MOA survey, microlensing observations in astrophysics, using a dedicated 1.8-meter telescope at Mount John University Observatory in New Zealand. Their goal was to detect dark objects in the Milky Way by watching for gravitational microlensing events. Gravitational microlensing is one of the most elegant applications of Einstein's general relativity. Einstein showed in 1915 that mass warps space-time, and light traveling through this warped space-time follows curved paths. When a massive object passes almost directly between Earth and a distant background star, the intervening object's gravity bends and focuses light from the background star, making it appear temporarily brighter. The effect is like a natural magnifying glass moving across the sky. The beauty of microlensing is that it works for any massive object: stars, brown dwarfs, planets, even black holes. The lensing object doesn't need to emit any light. You're detecting it purely through its gravitational influence on light passing nearby. The duration and shape of a microlensing event encode information about the lensing object's mass and distance. More massive objects create stronger lensing effects that last longer. Less massive objects create weaker, briefer events. By carefully analyzing the light curve, how the background star's brightness changes over time, you can determine the lensing object's mass. Suomi's team monitored tens of millions of stars in the galactic bulge, the dense central region of the Milky Way. They chose this region because it's packed with stars, providing a rich background screen of stars that could potentially be lensed. Every night for years, their telescopes scanned the same fields, measuring the brightness of every star, comparing to previous nights, searching for the telltale brightening of microlensing. Most nights showed nothing unusual. Stars appeared at their normal brightness, exactly as expected. The universe was stable and predictable. But occasionally, a star would brighten. The telescope's software would flag it automatically. Astronomers would examine the light curve, determine if it was a genuine microlensing event or some other phenomenon, variable stars, novae, instrumental artifacts, and if genuine, calculate the mass of the lensing object. Over the course of their survey, from 2006 to 2007, they detected hundreds of microlensing events. Most were caused by stars, faint red dwarfs or brown dwarfs passing in front of brighter background stars. The events lasted weeks or months, and the calculated masses were stellar: 0.1 to 0.5 solar masses for red dwarfs and 0.01 to 0.08 solar masses for brown dwarfs. But they also found 10 events that were completely different, anomalous, strange, deeply puzzling until they understood what they were seeing. These 10 events were brief, not weeks or months, but hours or days. One lasted less than 2 days, another lasted about 4 days. The briefest was over in about 18 hours. Brief events mean small masses. When the team calculated the masses of the objects causing these 10 events, they found something extraordinary. Between 0.3 and 3 Jupiter masses, firmly in the planetary mass range. These were not stars, they were not brown dwarfs, they were planets. But here's what made them revolutionary. What made them fundamentally different from the thousands of exoplanets detected orbiting other stars. These lensing events showed no evidence of a host star. When a planet orbiting a star causes a microlensing event, the signal has a characteristic pattern. The star's gravity creates the main brightening, and the planet creates a secondary spike or anomaly superimposed on that main curve. It's a distinctive double peak or spike plus bump pattern that immediately tells you planet plus star orbiting together. These 10 events showed nothing like that, just a single smooth brightening curve, rising and falling in a pattern consistent with a lone planet. No host star, no stellar companion, no evidence of orbital motion. The team considered every alternative. Maybe the planet was in an extremely wide orbit around a distant star, so far from the star that the star's lensing signature didn't overlap with the planet's during the observation. Maybe the star was too faint to produce a detectable lensing signal. Maybe observational gaps, cloudy nights, daylight, caused them to miss the stellar component. Statistical analysis ruled out all these alternatives. If these planets were all in wide orbits around stars, probability says the team should have detected at least a few cases where both the planet and its host star produced overlapping microlensing signals. They should have seen 2 or 3 planet plus star events among the 10 planetary events. They saw 0, not 1. The most straightforward explanation, the one that required the fewest additional assumptions, these 10 objects were free-floating planets, rogue planets, wandering the galaxy alone, with no host star, no orbital companion, no connection to any stellar system.
Detecting 10 rogue planets might seem like a small sample. How can you make sweeping conclusions about the entire galaxy from just 10 objects? The answer lies in statistical analysis and understanding survey sensitivity. Sumi's team knew precisely how sensitive their survey was. They knew how many stars they monitored, about 50 million, for how long, 2 years, and across what area of sky, several square degrees pointed at the galactic bulge. They knew what masses they could detect, down to about 0.3 Jupiter masses for typical event durations, and they knew the probability of detecting a microlensing event as a function of the lensing object's mass, distance, and velocity. With this information, they could work backwards. If they detected 10 planetary mass microlensing events with no stellar companions in their 2-year survey of 50 million stars, how many free-floating Jupiter mass planets must exist in the surveyed volume of space to produce 10 detections? The calculation is complex, involving detailed Monte Carlo simulations of microlensing detection probability, but the basic logic is straightforward. Detection rate equals true population multiplied by detection efficiency. If you know the detection rate, 10 events, and the detection efficiency, calculable from survey parameters, you can solve for the true population. The result? Approximately 1.8 free-floating Jupiter mass planets per main sequence star in the galaxy. Let that number sink in. Not 0.18, not 0.018. 1.8 rogues per star, nearly 2. The Milky Way contains approximately 200 to 400 billion stars. Estimates vary depending on how you count faint red dwarfs and account for unseen stellar populations. If there are 1.8 rogue planets per star, that's 360 to 720 billion rogue Jupiter mass planets in our galaxy alone. Hundreds of billions of dark worlds drifting through space. But this estimate has several important caveats and limitations. First caveat, this number applies specifically to Jupiter mass rogues, 0.3 to 3 Jupiter masses. The survey was most sensitive to this mass range. Smaller planets, Saturn mass, Neptune mass, Earth mass, produce fainter, briefer microlensing signals that are harder to detect. The survey might have missed many smaller rogues. Second caveat, the survey was conducted in the galactic bulge, where stellar densities are higher than in the galactic disk where we live. It's possible rogue planets are more common in the bulge than elsewhere, though there's no obvious physical reason why this should be true. Most estimates assume rogue planets are distributed similarly to stars throughout the galaxy. Third caveat, some of the detected events might have been planets in extremely wide orbits, thousands of AU, around stars too faint or distant to produce detectable lensing signals. The team's statistical arguments suggest this is unlikely to account for all 10 events, but it might account for 1 or 2. Despite these caveats, subsequent surveys and improved statistical analyses have largely confirmed Sumi's result. If anything, the true number might be higher. Why? Because the mass distribution of planets appears to favor smaller masses. We see more Neptune mass planets than Jupiter mass ones, more Earth mass than Neptune mass, at least around stars where we can detect them. If this distribution continues for rogue planets, there might be 10 Earth mass rogues per star. 10 Earth mass rogues per star means 2 trillion Earth-sized dark worlds in the Milky Way. 2 trillion planets roughly the mass and size of Earth wandering through interstellar space in darkness. Some researchers think even this might be conservative. In 2021, a statistical reanalysis of multiple microlensing surveys suggested the true number could be as high as 20 Earth mass rogues per star when accounting for detection biases.
20 per star would mean 4 trillion Earth-mass rogue planets in the galaxy. 4 trillion worlds. To put this in more local, comprehensible terms, the nearest star to our Sun is Proxima Centauri, located 4.24 light-years away. If rogue planets have an average density similar to stars, and remember, there are roughly twice as many rogues as stars, then the volume of space between our Sun and Proxima Centauri likely contains dozens of rogue planets, not orbiting either star, just drifting through the interstellar void, invisible in the darkness. There could be a Jupiter-mass rogue planet 1 light-year from Earth right now. We wouldn't know unless it happened to pass in front of a background star in exactly the right position at exactly the right time for one of our microlensing surveys to catch it. There could be an Earth-mass rogue even closer, half a light-year away, well within what we might consider our solar system's extended neighborhood, completely invisible to every telescope we've built, detectable only by its gravitational effects. The space around us is crowded with invisible neighbors, dark wanderers, cosmic orphans, their surfaces frozen to temperatures that would turn nitrogen into snow and oxygen into metallic liquid. Some might be ancient, ejected billions of years ago from stellar systems that no longer exist, their parent stars long dead. Others might be relatively young, ejected only millions of years ago from nearby stellar nurseries, still cooling from the heat of formation. They're all around us, a hidden population, passing through our cosmic neighborhood on journeys that began far away and will continue far beyond, unaware and uncaring that a civilization of curious primates on one small planet has finally detected their existence and begun to ponder what they mean.
How does a planet become rogue? What sequence of events can tear a world away from its parent star and hurl it into the interstellar void? The answer lies in understanding the chaotic violence of planetary system formation, a process astronomers have only recently begun to appreciate in its full destructive glory. Mechanism 1. Gravitational scattering during formation. The most common pathway to rogue status is gravitational scattering between planets during the early turbulent period of planetary system formation. Stars form when massive clouds of gas and dust collapse under their own gravity. As the cloud contracts, conservation of angular momentum causes it to spin faster, and centrifugal forces flatten it into a rotating disk, a protoplanetary disk. At the center, material accumulates into a dense, hot protostar that will eventually ignite fusion and become a true star. In the disk, dust grains collide and stick together, gradually building up larger bodies. This accretion process is remarkably efficient. Over just a few million years, dust grains become pebbles, pebbles become boulders, boulders become kilometer-sized planetesimals, planetesimals merge into Moon to Mars-sized planetary embryos, and embryos collide and merge to form full-sized planets. But here's the key point. This process isn't neat or orderly. Dozens or even hundreds of planetary embryos can form, scattered throughout the disk at various distances from the star. They don't all survive. In fact, most don't. When two planetary embryos' orbits cross or come close to crossing, and this is almost inevitable in a system with many embryos, they can have a close gravitational encounter. During such an encounter, the gravitational forces between the embryos redistribute orbital energy and angular momentum. The mathematics is governed by the conservation laws of physics. Total energy and total angular momentum must be conserved, neglecting losses to tidal heating or gas drag, which are usually small. But how that energy and momentum is distributed between the two bodies can change dramatically. One embryo typically gains energy. Its orbit becomes higher, faster, more energetic. The other loses energy. Its orbit drops lower, becomes tighter, more bound to the star. This is gravitational scattering, and it's a fundamental process in celestial mechanics. If the energy transfer is moderate, both embryos remain bound to the star, just in different orbits than before. If the transfer is extreme, one embryo can gain enough energy that its total orbital energy becomes positive. It reaches escape velocity and flies away from the star system forever. The embryo that escapes becomes a rogue planet. Computer simulations of this process, run thousands of times with different initial conditions to test statistical outcomes, consistently show that planetary systems with multiple giant planets almost always eject at least one planet during their first 100 million years. The systems start with more planets than can stably coexist in the available orbital space, and gravitational dynamics winnow the population down to stable survivors. The ejected planets are the casualties of this violent culling process. In 2011, the same year as Suomi's rogue planet discovery, planetary scientist Melvin Davies at Lund University published simulations showing that the typical planetary system likely ejects one planet for every giant planet that remains bound. Systems that end up with two giant planets probably started with 3 or 4. Systems with 3 giants probably started with 4 to 6. The rogues we detect aren't aberrations or cosmic accidents. They're the expected outcome of having too many planets forming too close together.
Mechanism 2. Stellar encounters. Stars aren't born in isolation. They form in clusters where hundreds or thousands of stars condense from the same giant molecular cloud over just a few million years. In these dense clusters, stars are packed much more closely than in the galactic field where we live now. In a typical young cluster, the average distance between stars might be only 0.1 to 0.5 light years, 10 to 50 times closer than the nearest star to our Sun. At these close spacings, stellar encounters are common. When two stars pass within a few thousand AU of each other, close enough that their gravitational influences overlap significantly, the encounter can disrupt planetary orbits. Planets that were stably orbiting one star can be perturbed onto eccentric orbits, transferred to the other star, or ejected entirely. The probability of ejection depends on the encounter geometry, the stellar masses, the approach velocity, and the planetary orbit's initial characteristics. Detailed simulations by Hagai Peretz and collaborators show that about 3 to 6% of planets in dense clusters get ejected due to stellar encounters over the cluster's first 100 million years. This might sound like a small fraction, but consider that most stars form in clusters. Over the galaxy's history, trillions of close stellar encounters have occurred, each one potentially scattering planets. The ejected planets from stellar encounters have a different velocity distribution than those ejected by planet-planet scattering. Stellar encounters can impart higher velocities, up to 100 kilometers per second or more, because the encounter involves stellar mass objects. These high-velocity rogues might eventually escape the galaxy entirely, wandering intergalactic space. Mechanism 3. Supernova ejection. The most violent ejection mechanism involves the death of massive stars in supernova explosions. When a star more than about 8 solar masses exhausts its nuclear fuel, its core collapses catastrophically in less than a second, triggering a supernova explosion. The star releases 10 to the 44th joules of energy, more energy than the Sun will release over its entire 10 billion-year lifetime in a matter of seconds. The blast wave expands at tens of thousands of kilometers per second. Planets close to the star are vaporized. Anything within a few AU of a supernova doesn't survive as a planet. It's heated to millions of degrees and blasted into plasma. But planets in outer orbits, tens or hundreds of AU away, can survive the blast. They're heated and irradiated intensely. Their atmospheres might be stripped away, their surfaces sterilized by X-rays and gamma rays, but the rocky or icy core remains intact. And here's the key point. The supernova suddenly removes most of the star's mass. A star that was 20 solar masses becomes a neutron star of only 1.5 solar masses. The remaining 18.5 solar masses is ejected into space. For planets orbiting this star, the sudden mass loss means they're suddenly moving too fast for the reduced gravity to hold them. They're like cars on a circular track, where the track suddenly becomes much weaker. They fly off on hyperbolic trajectories. The velocity they achieve depends on their orbital velocity before the supernova. A planet that was orbiting at 50 kilometers per second around a 20 solar mass star will find itself moving at essentially the same 50 kilometers per second around a 1.5 solar mass neutron star. But escape velocity at that distance from a 1.5 solar mass object is much lower than 50 kilometers per second. The planet escapes. These supernova-ejected rogues are the fastest, the most violent in origin. They race through the galaxy at velocities high enough to eventually escape the Milky Way's gravity entirely. They're the most extreme example of rogue planets, not just orphaned, but violently expelled at hypervelocity, carrying the scars of their traumatic birth in the form of radiation damage, atmospheric loss, and surface disruption.
The idea that planets can be ejected isn't just theoretical. We have evidence suggesting it happened in our own solar system's history. The evidence comes from multiple independent sources that, when combined, paint a picture of our solar system undergoing violent dynamical instability in its past, an instability that likely ejected at least one planet and dramatically rearranged the orbits of the survivors. The NICE model. In 2005, a team of planetary scientists including Rodney Gomes, Harold Levinson, Alessandro Morbidelli, and Cleomenes Tsiganis published a series of papers describing what became known as the NICE model, named after the French city where much of the work was done. The NICE model proposes that the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in a more compact configuration than we see today, with all four giants between about 5 and 15 AU from the Sun. Beyond them lay a massive disk of icy planetesimals, the remnants of planetary formation, billions of small icy bodies. For the first few 100 million years, this configuration was relatively stable, but it was metastable, stable against small perturbations, but vulnerable to orbital resonances that could trigger instability. Around 600 million years after the solar system's formation, about 3.9 billion years ago, Jupiter and Saturn crossed a 2-to-1 orbital resonance. Jupiter's orbital period became exactly twice Saturn's. This resonance amplified gravitational interactions between them, pumping up orbital eccentricities and triggering chaos. The giant planets began to gravitationally scatter each other. Jupiter migrated inward slightly. Saturn was pushed outward. Uranus and Neptune were flung outward dramatically. Uranus might have formed closer to the Sun than Neptune and been scattered farther out during this instability. As the giants migrated, they plowed through the disk of icy planetesimals, scattering billions of them. Some were flung into the inner solar system, causing the late heavy bombardment, a spike in impact rates recorded in lunar craters and dated to about 3.9 billion years ago. Others were ejected from the solar system entirely, becoming interstellar objects. The NICE model explains many features of the solar system that simple formation-in-place models struggle with: why Neptune is farther from the Sun than Uranus, despite being more massive; why the Kuiper Belt, the region beyond Neptune containing Pluto and similar objects, has its current structure; why the asteroid belt has certain features; why the late heavy bombardment occurred when it did. But some versions of the NICE model have an even more dramatic implication: a fifth giant planet.
Computer simulations of the nice-modeled instability show that starting with 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, produce outcomes that don't quite match the solar system's current architecture. The planet's final eccentricities and the Kuiper belt structure don't match observations perfectly. But simulations that start with 5 giant planets, 4 that we see, plus 1 additional ice giant, similar to Uranus or Neptune, produce much better matches. In these simulations, the 5th planet is ejected entirely during the instability, carrying away excess energy and angular momentum, allowing the remaining 4 to settle into orbits closely matching what we observe. The evidence isn't definitive, but it's suggestive. If a 5th giant planet existed and was ejected 3.9 billion years ago, where is it now? Somewhere in the Milky Way, long gone, traveling probably 10 to 20 kilometers per second relative to the Sun, fast enough to escape but not hypervelocity. It could be hundreds or even thousands of light years away by now, completely untraceable. If you could somehow find it and analyze its composition, you'd find isotopic ratios and chemical signatures matching solar system material. You'd know it formed in our system. But finding it is essentially impossible. It's one dark planet among billions of dark planets scattered across the galaxy, with no remaining connection to its origin. We might have a lost sibling world wandering out there, a world that once orbited our Sun, that might have been in resonance with Jupiter or Saturn in the solar system's early days, that was violently ejected and has been drifting through the galaxy for nearly 4 billion years. It's a humbling thought. Our solar system isn't special, isn't immune to the chaos that seems to characterize planetary system formation. We too have scattered our planets, ejected our worlds, undergone violent instabilities. We're just fortunate that Earth wasn't the planet that got thrown out. But the evidence forces us to confront an uncomfortable possibility. The universe contains far more planets than we ever imagined, and the vast majority of them drift in eternal darkness, untethered from any sun, wandering the galaxy on journeys that may last until the heat death of the universe itself.
Microlensing is extraordinarily powerful for detecting rogues, but it has a fundamental limitation. Each detection is a one-time event lasting hours or days. Once the lensing event ends, the planet continues on its way, disappearing back into the darkness. You can't follow up, can't get more detailed information, can't study the object's properties beyond mass and approximate distance. But there's another way to find rogue planets, at least young ones: direct infrared imaging. The physics behind this is straightforward but profound. When planets form, the process generates enormous heat. Gravitational potential energy is converted to thermal energy as material falls onto the growing planet. Essentially, the process of falling creates heat. Massive collisions between planetesimals release kinetic energy that becomes heat. The entire accretion process is violent and energetic. A newly formed Jupiter-mass planet has a surface temperature of perhaps 1,000 to 1,500 Kelvin, hot enough to glow dull red if you could see it. Over time, this formation heat radiates away into space, and the planet cools. But cooling is a slow process for a planet-sized object with no star nearby to equilibrate with. A Jupiter-mass planet takes about 100 million years to cool from its formation temperature down to about 500 K, another 100 million years to cool to 300 K, another few hundred million years to cool to the equilibrium temperature in deep space, about 30 to 50 K, depending on the galactic background radiation and internal heat from radioactive decay. During this cooling phase, roughly the first few hundred million years, the planet emits significant infrared radiation. Its luminosity is feeble by stellar standards, perhaps 1 million times fainter than the Sun, but it's detectable with sensitive infrared telescopes if the planet is close enough. This is the principle behind direct imaging of young exoplanets. Planets like HR 8799b, C, D, and E, Beta Pictoris b, and 51 Eridani b have all been directly imaged in infrared light because they're young,
10 to 100 million years old, and still warm from formation. The same technique works for rogue planets, with one crucial advantage: there's no bright host star to overwhelm the planet's faint infrared glow. A young rogue planet appears as an isolated point source of infrared radiation against the background sky. The challenge is distinguishing it from other faint infrared sources, distant galaxies, background stars, brown dwarfs, asteroids in our solar system reflecting sunlight. The solution? Spectroscopy and multi-wavelength imaging. By measuring the object's brightness at multiple infrared wavelengths and taking spectra that reveal absorption features from molecules in its atmosphere, you can determine whether the object is a planet, a brown dwarf, a distant galaxy, or something else. CFBD SIR 2149-0403, the first directly imaged rogue planet. In 2012, a team led by Philippe Delorme using the Canada-France-Hawaii telescope made a landmark discovery, CFBD SIR 2149-0403, a rogue planet candidate about 100 light-years from Earth. The object was detected through a systematic infrared survey searching for faint red objects, objects bright in infrared but invisible or nearly invisible in visible light. When the team identified CFBD SIR 2149, they obtained follow-up infrared spectra using larger telescopes. The spectra were remarkable. They showed strong absorption from water vapor, methane, and other molecules characteristic of cool, planet-like atmospheres. The temperature was estimated at about 400 degrees Celsius, hot by terrestrial standards, but cool for a self-luminous object, consistent with a young planet still radiating formation heat. The mass was estimated at 4 to 7 Jupiter masses based on evolutionary models that connect luminosity, temperature, and mass to mass. This is firmly in the planet mass range, too small to be a brown dwarf. But the most compelling evidence came from its motion through space. By measuring the object's position carefully over months and comparing to archival images, astronomers calculated its velocity and direction. CFBD SIR 2149 is moving at about 10 to 15 kilometers per second relative to the Sun, in a direction consistent with membership in the AB Doradus Moving Group. The AB Doradus Moving Group is a collection of about 30 young stars, 30 to 50 million years old, that all formed together in the same star-forming region and are now slowly drifting apart as they orbit the galaxy. They're not gravitationally bound, they're just stars that happen to be traveling in roughly the same direction because they had a common origin. If CFBD SIR 2149 is a member of this moving group, and the velocity match is excellent, then it's 30 to 50 million years old, formed in the same stellar nursery as the AB Dor stars, and somehow was ejected to become a rogue. This was powerful confirmation of the microlensing results using a completely independent technique. Rogues exist. They can be directly detected. They're real. PSO J318.5/22, a rogue with detailed atmospheric characterization. The next major direct imaging discovery came in 2013. Michael Liu and collaborators at the University of Hawaii, using the Pan-STARRS Survey Telescope, discovered PSO J318.5/22, a young, free-floating planet about 80 light-years away. PSO J38 is remarkable for its youth and the detail with which it's been studied. At only 12 million years old, based on membership in the Beta Pictoris moving group, it's one of the youngest known rogue planets. This youth makes it relatively bright in infrared, surface temperature about 800 degrees Celsius, hot by terrestrial standards, but cool for a self-luminous object, consistent with a young planet still radiating formation heat. Using the NASA Infrared Telescope on Mauna Kea, Liu's team obtained high-quality spectra covering the near-infrared wavelength range. The spectra revealed
strong water vapor absorption bands, methane absorption features, possible carbon monoxide absorption, a spectral energy distribution, how brightness varies with wavelength, matching theoretical models of giant planet atmospheres. Most intriguingly, the spectral features of PSO J318 closely match those of directly imaged exoplanets orbiting stars, planets like Beta Pictoris b and HR 8799c. This was powerful evidence that PSO J318 is a planet in every meaningful sense. Same mass, same composition, same formation mechanism that simply happens to lack a stellar companion. The team also measured PSO J318's infrared colors with exquisite precision. Infrared color refers to the ratio of brightness at different infrared wavelengths. For instance, how bright the object appears at 1.2 microns versus 2.2 microns. These color measurements are diagnostic of temperature and atmospheric properties. PSO J318's colors placed it right in the middle of the sequence of known directly imaged giant planets, clearly separated from the sequence of brown dwarfs. It's planetary, not stellar, in its properties. Follow-up observations over multiple years have also revealed variability. PSO J318's infrared brightness changes by a few percent over timescales of hours. The most likely explanation, clouds in its atmosphere. As the planet rotates, probably with a period of several hours, similar to Jupiter's 10-hour rotation period, regions with thick clouds rotate into view, causing the observed brightness to vary. We're observing weather patterns on a rogue planet, clouds forming and dissipating in an atmosphere that will never see sunlight. Atmospheric circulation driven by internal heat, creating wind patterns and pressure systems in eternal darkness. It's one of the most alien environments we've ever studied. The James Webb Space Telescope. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, has transformed the field of directly imaging young rogues. JWST's unprecedented infrared sensitivity, roughly 100 times better than previous space telescopes like Spitzer, means it can detect cooler, older, fainter rogues than ever before possible. A planet that's 100 million years old and cooled to 200 K might be invisible to previous telescopes, but detectable to JWST. In 2023, one of JWST's first major survey programs targeted the Orion Nebula, a nearby star-forming region where thousands of stars are currently being born, located about 1,350 light-years from Earth. The Orion Nebula survey used JWST's near-infrared camera to image the entire nebula in multiple infrared wavelengths. The results were astounding. Dozens of free-floating planetary mass objects detected. Objects with estimated masses between 0.6 and 13 Jupiter masses. The 13 Jupiter mass upper limit is where deuterium fusion begins, marking the boundary between planets and brown dwarfs. All young, only 1 to 2 million years old, all still glowing brightly in infrared from formation heat. The sheer number was striking. In just one star-forming region, in just the portion surveyed by JWST, dozens of planetary mass objects floating freely. This suggested that either planetary ejection is extraordinarily common during formation, or many of these objects formed in isolation directly from the collapse of small gas clumps, never orbiting a star from the beginning. The debate over formation mechanism continues. Some of the detected objects might be extremely low-mass brown dwarfs formed by direct gas cloud collapse. Others are almost certainly ejected planets. Distinguishing between these formation pathways requires detailed mass measurements and comparisons to theoretical models, work that's still ongoing. But regardless of formation mechanism, the functional outcome is the same. planetary mass objects existing independently in space, governed by the same physics, subject to the same evolutionary processes as planets orbiting stars. Even more intriguingly, some of the Orion free-floating objects show evidence of disks of gas and dust surrounding them, similar to protoplanetary disks around young stars, but much smaller. These disks might be forming moons, satellites orbiting the rogue planet, creating miniature planetary systems without a star. Imagine a Jupiter-mass world drifting through interstellar space, surrounded by a disk from which multiple Moon to Mars-sized satellites are condensing, creating a complete system of planet and moons, all wandering together through the galaxy in darkness. JWST has the spectroscopic capability to study these systems in detail, potentially detecting water vapor, methane, and other molecules in both the planet's atmosphere and in the disk material. Over the coming years, as more observations accumulate, we'll build a comprehensive picture of what young rogue planets look like, how they evolve, and what their immediate environments contain.
Direct imaging gives us detailed information about individual young rogues, but it's inherently biased toward the youngest, warmest, nearest objects. The vast majority of rogues, ancient, cold, distant, remain completely invisible to direct imaging. To understand the true population, we need statistical analyses combining multiple surveys with different detection techniques and sensitivities. Microlensing survey results. The OGLE survey, optical gravitational lensing experiment, operating continuously since 1992, has accumulated the largest dataset of microlensing events. Based in Chile, OGLE monitors over 1 billion stars toward the galactic bulge every clear night. By 2023, OGLE had detected over 20,000 microlensing events total. Most are stellar, stars or brown dwarfs lensing background stars. But embedded in this dataset are dozens of planetary events, both planets orbiting stars and free-floating planets. Statistical analyses of the OGLE dataset, published in multiple papers between 2018 and 2023, refined the rogue planet frequency estimates. Jupiter mass rogues, 0.5 to 5 Jupiter masses, 2 to 4 per main sequence star. Saturn/Neptune mass rogues, 0.05 to 0.5 Jupiter masses, 4 to 8 per star. Earth mass rogues, 0.5 to 5 Earth masses, uncertain, possibly 10 to 50 per star. These numbers come with large error bars, factors of 2 or 3 uncertainty, because small planets produce brief, faint events that are easy to miss. But the central values suggest rogues outnumber stars significantly, possibly by an order of magnitude when you include all masses. The mass distribution appears to follow a similar pattern to planets orbiting stars. Smaller masses are more common. This makes sense if rogue planets form via the same accretion process as regular planets and are subsequently ejected. You'd expect more small planets because that's what the formation process naturally produces. Detection bias corrections. Understanding detection biases is crucial for accurate population estimates. Every survey has selection effects, types of objects it's more or less likely to detect. For microlensing, the main biases are mass bias. More massive planets create longer duration events that are easier to detect. Detection efficiency sharply drops for masses below Earth mass. Distance bias. Lensing events for nearby objects are less likely because there are fewer background stars at the right distances and geometries. The surveys are most sensitive to rogues at distances of a few kiloparsecs, thousands of light years. Velocity bias. Fast-moving rogues create briefer events. If a rogue is moving at 100 kilometers per second instead of 30 kilometers per second, its lensing event is 3 times shorter and easier to miss. Temporal coverage bias.
Events are only detected if they occur when the survey is observing. A one-day event that happens during a cloudy night or during daylight hours is missed. Researchers use detailed Monte Carlo simulations to quantify these biases. They simulate millions of rogue planets with various masses, distances, and velocities, calculate which ones would produce detectable lensing events given the survey's observing pattern, and determine the detection efficiency as a function of planet properties. These corrections are then applied to the observed event rate to infer the true population. The uncertainties are large, factors of 2 to 3 are typical, but the central values are robust across different analyses and different surveys. Implications for galactic mass budget. If there are truly 10 to 20 rogues per star, including all masses, this has significant implications for the galactic mass budget. The total stellar mass in the Milky Way is roughly 6 times 10 to the 10 solar masses, 60 billion solar masses. If there are 20 planets per star with an average mass of, say, 10 Earth masses, a weighted average across the mass distribution, that's 200 Earth masses per star in rogue planets. 200 Earth masses is about 0.006 solar masses. Multiply by the number of stars, say 200 billion, and you get total mass in rogue planets approximately 0.006 times 200 billion equals 120 million solar masses. That's roughly 0.2% of the galaxy's stellar mass. Not dominant, but not negligible either. For comparison, the total mass in planets orbiting stars is probably similar or slightly higher, so the combined planet population, orbiting plus rogue, might be 0.3 to 0.5% of stellar mass. Interestingly, this is comparable to the estimated mass in the interstellar medium, gas and dust between stars, in the galactic disk. Rogue planets are a significant reservoir of heavy elements, carbon, oxygen, silicon, iron, locked up in solid form and distributed throughout the galaxy. Over billions of years, collisions between rogues and other objects, plus tidal disruption when rogues pass very close to stars, return some of this material to the interstellar medium, contributing to galactic chemical evolution.
Rogue planets aren't stationary. They move through the galaxy with velocities inherited from their ejection events and their parent stars' galactic orbits. Understanding these velocities tells us about formation mechanisms and long-term evolution. Typical velocities. Most rogues detected via microlensing or inferred from statistical analyses have velocities in the range of 20 to 50 kilometers per second relative to the local standard of rest, the average velocity of stars in our galactic neighborhood. This range makes sense given the ejection process. When a planet is ejected via gravitational scattering, it leaves the system at escape velocity plus some excess. Escape velocity from the outer solar system at 30 AU, Neptune's distance, is about 8 kilometers per second. Add 10 to 20 kilometers per second from the scattering encounter, and you get a rogue moving at 18 to 28 kilometers per second relative to its parent star. The parent star itself is moving at some velocity through the galaxy. In our neighborhood, stellar velocities relative to the local standard of rest range from 10 to 40 kilometers per second in random directions. Add the star's velocity to the ejection velocity, and typical rogues end up moving at 20 to 50 kilometers per second. This velocity range has important consequences. Galactic confinement. Rogues with velocities below about 200 kilometers per second are gravitationally bound to the Milky Way. They'll orbit the galactic center indefinitely, crossing through the disk and halo repeatedly. Crossing timescales, at 30 kilometers per second, a rogue travels 1 light-year every 10,000 years. To cross the entire galaxy, 100,000 light-years, takes 1 billion years. Rogues are slow by cosmic standards. Encounter rates. The encounter rate with stars depends on velocity and stellar density.
In the galactic disk, a rogue at 30 kilometers per second passes within 1 AU of a star on average every few billion years, rare enough that most rogues never have close stellar encounters. Hypervelocity rogues. But some rogues move much faster. Hypervelocity rogues with velocities exceeding 100 kilometers per second have been detected or inferred from unusual microlensing events. These high velocities can't be explained by normal planet-planet scattering. They require more extreme acceleration mechanisms. Supernova acceleration. When a massive star explodes, planets at intermediate distances can be accelerated to 100 to 200 kilometers per second by the sudden loss of stellar mass, combined with possible direct momentum transfer from the supernova blast wave. Black hole encounters. If a planetary system passes within a few hundred AU of a stellar mass black hole, the extreme gravitational gradients can accelerate planets to very high velocities through slingshot effects. Neutron star close approaches. Similar to black holes, close encounters with neutron stars can impart large velocity kicks. Hypervelocity rogues are fascinating because they're on escape trajectories from the galaxy. At 150 kilometers per second, a rogue can overcome the Milky Way's gravitational binding. Over tens or hundreds of millions of years, it will leave the galaxy entirely, entering the intergalactic void. In 2018, Lauren Weiss and collaborators reported a possible hypervelocity rogue candidate moving at approximately 180 kilometers per second based on microlensing characteristics and proper motion measurements. If confirmed, this object will eventually escape the Milky Way and wander the space between galaxies. Imagine the journey. Ejected from its home system by a supernova 100 million years ago, this planet has traveled tens of thousands of light years already. Over the next 100 million years, it will cross the remaining distance to the galactic edge, pass through the halo, and finally leave the gravitational pull of the Milky Way. Eventually, in billions of years, it might approach another galaxy, Andromeda perhaps, or one of the local group dwarfs. It could be captured by a star in that galaxy, ending its intergalactic journey and beginning a new life as an exoplanet in an alien stellar system. Or it might drift in intergalactic space forever, traveling through the expanding voids between galaxy clusters, a lone world in the truest sense, separated from the nearest star by millions of light years. Velocity as a diagnostic. Velocity measurements provide clues about formation mechanisms. Rogues with low velocities, 15 to 30 kilometers per second, likely formed via gentle planet-planet scattering. Those with moderate velocities, 30 to 80 kilometers per second, might have been ejected in more violent encounters or from multiple scattering events. Hypervelocity rogues, above 100 kilometers per second, almost certainly experienced supernova acceleration or encounters with compact objects. By measuring the velocity distribution of the rogue population, what fraction are at each velocity range, we can infer the relative importance of different ejection mechanisms across galactic history. Future surveys, particularly Roman Space Telescope with its exquisite astrometry, will measure rogue velocities for hundreds or thousands of objects, providing unparalleled statistical power for understanding formation pathways. But this represents just one piece of a much larger puzzle, hidden in the violent dynamics of planetary formation and evolution across billions of years of galactic history.
The existence of rogue planets in such vast numbers forces a fundamental reconception of planetary system formation. For most of the 20th century, astronomers developed theories based on our solar system's apparent orderliness. The nebular hypothesis suggested planets form from a disk, accrete material, and settle into stable orbits where they remain for billions of years. Our solar system seemed to fit this picture. Orderly spacing, nearly circular orbits, all planets orbiting in the same direction in nearly the same plane. The discovery of exoplanets and rogue planets has shattered this comfortable illusion. Planetary systems aren't static. They're dynamic, violent, and unstable during their formative years. The gravitational n-body problem. At the heart of this chaos lies a famous problem in classical mechanics, the gravitational n-body problem. For two bodies, like a single planet orbiting a star, Newton's laws give exact solutions. The orbit is an ellipse, period. The planet follows this ellipse indefinitely, predictably, perfectly. For three bodies, a star and two planets, no general closed-form solution exists. The system exhibits deterministic chaos. Tiny differences in initial conditions lead to vastly different outcomes over time. Long-term predictions become impossible. For n-bodies, many planets, the chaos is even more extreme. Modern planetary system formation simulations use supercomputers to numerically integrate the equations of motion for hundreds or thousands of bodies, gas giants, planetary embryos, planetesimals embedded in a gas disk, evolved forward in time step by tiny step. These simulations consistently reveal violent evolution. Phase 1, 0 to 5 million years, dust coagulates into planetesimals. Thousands of kilometer-sized bodies form throughout the disk. Phase 2, 5 to 30 million years, planetesimals collide and merge, forming dozens of planetary embryos, Moon to Mars mass. The gas disk is still present, causing the embryos to migrate. Phase 3, 30 to 100 million years, the gas disk dissipates. Embryos now interact purely through gravity. Close encounters become frequent. The system undergoes instability. Some embryos collide and merge, forming fewer, larger planets. Others are rejected entirely. Phase 4, 100 million to 1 billion years, the system settles into a stable configuration. The surviving planets have cleared their orbital zones of competitors. Smaller debris, asteroids, comets, remains but doesn't threaten planetary stability. The critical insight: Phase 3 almost always involves ejections. Systems that start with 10 to 20 embryos typically end with 3 to 5 planets plus several ejected rogues. Orbital resonances and instability. A key driver of instability is orbital resonance. A resonance occurs when two bodies' orbital periods have a ratio of small integers, 2 to 1, 3 to 2, 5 to 3, etc. Near resonances, gravitational interactions repeat at the same orbital phases, allowing small forces to accumulate over many orbits. This can stabilize orbits, as with some moon systems, or destabilize them catastrophically. Jupiter and Saturn are currently near a 5 to 2 resonance. Jupiter orbits 5 times, while Saturn orbits twice. In the NICE model, crossing a 2 to 1 resonance triggered the solar system's late instability. In newly forming systems with many planets, resonances are almost inevitable. As planets migrate through the gas disk, they sweep through resonances with each other. Some passages are gentle, others trigger chaos. Computer simulations by Alessandro Morbidelli and colleagues show that systems with 3 or more giant planets between 0.5 and 5 AU almost always undergo resonance-triggered instabilities within 100 million years. Migration, the double-edged sword. Planet migration, the gradual change in orbital distance due to gravitational interactions with the gas disk, adds another layer of complexity. A planet massive enough to open a gap in the gas disk, typically a few Earth masses or more, feels gravitational torques from the disk material. These torques cause the planet to spiral inward, type 2 migration, or outward, rarer, depends on disk properties. Migration allows planets to move into regions with more material, growing larger, but it also disrupts other planets' orbits. As a migrating planet crosses orbital paths of pre-existing planets, close encounters occur. The result? Some merge, some are pushed into different orbits, some are ejected. Hot Jupiters, Jupiter-mass planets orbiting extremely close to their stars, periods of days rather than years, almost certainly formed farther out and migrated inward. During their inward journey, they likely scattered other planets, ejecting them as rogues. Every hot Jupiter we detect might represent 2 to 3 ejected planets from that system.
The role of mass and configuration. Not all planetary systems eject planets at the same rate. The ejection probability depends on number of planets. More planets mean more potential interactions and higher ejection rates. Mass distribution. Systems with one dominant massive planet, like our Jupiter, are more stable. Systems with multiple comparable mass giants are more likely to eject planets. Orbital spacing. Tightly packed systems are more unstable. Spacing measured in mutual Hill radii, the radius within which a planet's gravity dominates, determines stability. Systems with planets spaced less than 10 mutual Hill radii are typically unstable. Eccentricities. Higher eccentricities mean orbits cross easier, increasing encounter rates and ejection probabilities. Simulations suggest that the typical planetary system might eject 30 to 50% of its initially formed planets. Systems that end up with stable configurations matching observed exoplanet statistics typically started with 2 to 3 times more planets than they currently have. The rogues we detect aren't aberrations. They're the expected casualties of a violent winnowing process.
Now we arrive at one of the most profound, unsettling, and fascinating questions raised by the discovery of rogue planets. Could they harbor life? The question seems absurd at first. Life requires energy. On Earth, nearly all energy ultimately comes from the sun through photosynthesis. Plants and algae capture sunlight, convert it to chemical energy, and this energy flows through the ecosystem, from plants to herbivores to carnivores to decomposers. Rogue planets receive essentially zero sunlight. They drift through interstellar space in darkness. Surface temperatures hover around 30 Kelvin. At these temperatures, all known biochemistry halts. Water freezes into ice harder than steel. Even carbon dioxide and nitrogen freeze solid. No liquid, no chemical reactions, no life. But we need to look beneath the surface. Earth's internal heat engine. Earth isn't warmed solely by the sun. Our planet has substantial internal heat from 2 sources. Residual formation heat. When Earth formed 4.6 billion years ago, gravitational potential energy converted to thermal energy. Planetesimals falling onto the growing Earth released kinetic energy as heat. Giant impacts, including the moon-forming impact, contributed enormous heat. The planet started hot, possibly with a surface magma ocean, and has been slowly cooling ever since. Radioactive decay. Earth's mantle and crust contain radioactive isotopes, primarily uranium-238, thorium-232, and potassium-40. These elements decay slowly, half-lives of billions of years, releasing heat continuously. The total heat flow from Earth's interior to the surface is approximately 47 terawatts, 47 trillion watts of continuous power. This is vastly less than the 174,000 terawatts we receive from the sun, but it's still substantial. This internal heat drives crucial processes. Plate tectonics, the slow convection of Earth's mantle powered by internal heat, causes crustal plates to move, creating earthquakes, volcanoes, mountain building, and oceanic trenches. Volcanism. Magma from the mantle erupts at plate boundaries and hotspots, bringing heat and chemicals from the interior to the surface. Hydrothermal circulation. Seawater percolates through oceanic crust, is heated by subsurface magma, and erupts at hydrothermal vents on the ocean floor. Deep-sea hydrothermal ecosystems. In 1977, scientists exploring the ocean floor using the submersible Alvin made a discovery that revolutionized biology: hydrothermal vents teeming with life. At the Galapagos Rift, 2,500 meters below the surface, where sunlight never penetrates and the water is perpetually dark and cold, they found entire ecosystems. Giant tube worms 2 meters long clustered around vents, clouds of shrimp,
beds of mussels and clams, bacterial mats coating the rocks. These ecosystems don't depend on photosynthesis. They depend on chemosynthesis, the use of chemical energy from dissolved minerals in the hot vent fluids to power metabolism. Bacteria oxidize hydrogen sulfide, methane, or molecular hydrogen, extracting energy from these redox reactions and using it to fix carbon dioxide into organic molecules. These chemosynthetic bacteria form the base of the food chain. Tube worms have symbiotic bacteria in their tissues that provide them with nutrients. Shrimp graze on bacterial mats. Predators feed on grazers. The entire ecosystem runs on Earth's internal heat, completely independent of the sun. The Stephenson model, liquid water on rogue planets. In 1999, Caltech planetary scientist David Stephenson published a paper titled Life-Sustaining Planets in Interstellar Space in the journal Nature. The paper presented detailed calculations showing that rogue planets could maintain subsurface liquid water for billions of years. Here's the key insight. A thick atmosphere acts as an insulating blanket, trapping internal heat. Consider an Earth-mass rocky planet ejected shortly after formation. The planet has internal heat from radioactive decay, 47 terawatts initially for Earth mass, a thick atmosphere captured from the protoplanetary nebula, perhaps 100 times Earth's current atmospheric mass, composed of hydrogen and helium.
As the planet drifts into interstellar space, it cools rapidly at first. But the thick hydrogen atmosphere is an excellent insulator. Hydrogen has very low thermal conductivity at low temperatures. The atmosphere's outer layers freeze. Nitrogen condenses and falls as snow. Carbon dioxide freezes into dry ice. Water vapor forms thick ice layers. Eventually, you have kilometers of ice covering the planet's surface. But beneath the ice, insulated from space, liquid water can persist. Stephenson's calculations showed that with an atmosphere of about 100 bars of hydrogen at the surface, compressed to much higher pressure in the deep atmosphere, a rogue Earth-mass planet could maintain a subsurface ocean for over 10 billion years. The temperature at the ice-water interface would be around 270 to 280 K, just below the freezing point of water. Pressure from overlying ice keeps the water liquid. Heat from radioactive decay in the mantle replenishes heat lost through slow conduction through the ice. It's a stable equilibrium. Ice insulates. Internal heat maintains temperature. Liquid water persists. Requirements for life on rogues. For life to exist on a rogue planet, we need liquid water, possible via the Stephenson mechanism, chemical energy, available from hydrothermal vents powered by the planet's interior heat, chemical building blocks, organic molecules, amino acids, nucleobases, lipids, present from the planet's formation or delivered by comets or asteroids before ejection, and stability. The environment must remain stable for long enough for life to originate and evolve. All four requirements can be met, at least in principle. Time is no obstacle. A rogue planet has billions of years, as much time as Earth has had. If life can originate in hydrothermal systems, as some theories suggest, a rogue planet provides ideal conditions. Radiation is no threat. Deep beneath ice, organisms are shielded from cosmic rays and galactic background radiation. The radiation environment is benign. Nutrients. Hydrothermal circulation through the rocky interior would dissolve minerals, providing sulfur, iron, phosphorus, and other elements necessary for biochemistry. The biggest question is origin. Can life start on a rogue planet, or must it originate on an illuminated world and then survive ejection? If life requires sunlight to originate, perhaps UV radiation to drive prebiotic chemistry, then rogue biospheres would be secondary. Life starts on a planet orbiting a star, the planet is ejected, and life adapts to the new environment. But if life can originate in dark hydrothermal systems, and this is a viable hypothesis consistent with current origin of life research, then rogue planets might be pristine habitats for abiogenesis. Implications for life in the universe. If even 0.1% of rogue planets harbor life, the implications are staggering. With potentially 10 trillion Earth mass rogues in the Milky Way, 0.1% means 10 billion living worlds, 10 billion biospheres drifting through the galaxy in darkness. Most life in the universe might exist on rogues, not on planets orbiting stars. Most biospheres might be isolated, cut off from any cosmic context, completely unaware that stars exist. If intelligence evolved on a rogue planet, an enormous if, given the isolation and lack of obvious selection pressures for intelligence, that civilization's worldview would be utterly alien. They might develop science, technology, even space travel, launching probes to the surface through the ice, but never astronomy. No telescopes, no cosmology. Their universe would be the ocean beneath the ice. Discovering the universe beyond, that they live on a planet, that stars exist, that the cosmos is vast, would be a revelation more profound than any human has experienced. It would be learning that reality extends infinitely beyond everything you thought possible. And we might never detect such civilizations. They're invisible, silent, radio quiet, drifting through space with no technological signatures we'd recognize.
Finding rogue planets is extraordinarily difficult. Detecting life on them is harder still, but progress is being made. The Roman Space Telescope Revolution. Launching in May 2027, the Nancy Grace Roman Space Telescope will transform rogue planet science. Roman's key advantage, a 2.4-meter mirror, same size as Hubble, with a field of view 100 times larger. This wide field enables microlensing surveys that would be impossible with narrow-field telescopes. Roman's planned microlensing survey will monitor hundreds of millions of stars in the galactic bulge continuously for at least 5 years. Detection estimates range from 500 to 5,000 rogue planets, depending on their true frequency. Critically, Roman will be sensitive down to approximately 0.1 Earth masses, Mars-sized rogues. This will finally nail down the mass distribution across the full planetary mass range. Each detection will provide mass from lensing duration and characteristics, approximate distance from lensing parallax if detectable, rough velocity from event duration and mass. Statistical analyses of Roman's hull will answer fundamental questions. What's the true frequency of rogues versus stars? Does the mass distribution follow the same pattern as planets orbiting stars? Are there regional variations in the galaxy? What fraction might have moons, detectable as additional features in lensing light curves? JWST spectroscopy of young rogues. For young rogues detected by direct imaging, JWST can obtain exquisite spectra, revealing atmospheric composition in unprecedented detail. JWST's spectroscopic instruments can detect water vapor absorption features, methane, ammonia, carbon monoxide, carbon dioxide, clouds via scattering features and variability, temperature profiles from pressure-broadened spectral lines, atmospheric dynamics via Doppler shifts if the planet rotates rapidly. For the nearest young rogues, within about 100 light-years, JWST might even detect biosignatures if they exist. Oxygen, phosphine, or other gases that require biological production could appear as absorption lines in the spectrum. The challenge is biosignatures are faint. Oxygen absorption might contribute only 1 to 2% of the total spectral signal. Detecting this requires signal-to-noise ratios of several hundred, which requires tens of hours of integration time. But for the nearest, brightest young rogues, it's feasible. A few dozen hours of JWST time could potentially detect oxygen in the atmosphere of a rogue planet if that oxygen is present at percent level abundances. Extremely Large Telescope Prospects. The Extremely Large Telescope, with its 39-meter segmented mirror, will directly image nearby rogues with resolution and sensitivity far exceeding current capabilities. For rogues within 20 light-years, the ELT could image the planet as a resolved disk, not just a point source, map surface features, if any are visible through the atmosphere, measure rotation periods from time series photometry, detect moons via direct imaging or astrometric wobble, obtain spectra at multiple wavelengths simultaneously. The ELT might even detect thermal emission from ancient cold rogues if they're close enough. A 10-billion-year-old Jupiter mass rogue at 10 light-years, cooled to perhaps 40 K, would be extraordinarily faint, but the ELT's collecting area and advanced adaptive optics might just barely detect it. Searching for moons and biosignatures. The Holy Grail, detecting life on a rogue planet. Direct detection of surface biospheres is impossible. Rogue surfaces are frozen wastelands at 30 K. But if subsurface life produces gases that leak into the atmosphere, those gases might be detectable. On Earth, oxygen is the classic biosignature. Our atmosphere is 21% oxygen entirely due to photosynthesis. Abiotic processes can produce traces of oxygen, but sustaining 21% requires continuous biological production. A rogue planet wouldn't have photosynthetic oxygen, no sunlight for photosynthesis, but subsurface life might produce other gases: methane from methanogenic microbes, hydrogen sulfide from sulfate-reducing bacteria, phosphine, possibly from microbial metabolism, though this is controversial, N2O or CH3Cl, produced by some bacteria. If these gases accumulate to detectable levels, percent level or even parts per million, spectroscopy might reveal them. The challenge is enormous. We're talking about detecting faint spectral features in the faint infrared glow of a distant, cold object. But within the next 10 to 20 years, technology might advance enough to make it possible. And if we succeed, if we detect biosignatures in the atmosphere of a rogue planet, it will revolutionize biology, astronomy, and philosophy simultaneously. We'll have confirmed that life doesn't require a star, that biospheres can persist in eternal darkness, that the cosmos might be filled with hidden life we never imagined. The evidence extends beyond mere detection statistics into the realm of habitability, the possibility of subsurface oceans harboring entire ecosystems, and the profound philosophical implications of life existing where we never thought to look.
To truly grasp how planets become rogues, we must understand the mathematics of orbital mechanics, the precise equations that govern gravitational interactions and determine when a planet escapes versus when it remains bound. Every object orbiting another object possesses orbital energy, a combination of kinetic energy from its motion and gravitational potential energy from its position in the gravitational field. The total orbital energy is given by E equals 1/2 mv squared minus gmm over r, where E equals total orbital energy, m is the mass of the orbiting planet, v is the orbital velocity, g is the gravitational constant, m is the mass of the star, and r is the distance from the star. The first term, 1/2 mv squared, represents kinetic energy, energy of motion. A planet moving faster has more kinetic energy. This term is always positive. The second term, minus gmm over r, represents gravitational potential energy. By convention, this is defined as 0 at infinite distance and becomes increasingly negative as the planet gets closer to the star. This represents the binding energy,
how much the planet is gravitationally bound to the star. For a stable, bound orbit, the total energy, E, is negative. The gravitational binding energy, negative term, outweighs the kinetic energy, positive term. The planet is trapped in the star's gravitational well, following an elliptical orbit indefinitely. But when two planets have a close encounter, when they pass within a few mutual Hill radii, gravitational forces between them can transfer energy from one planet to another. The Hill sphere, or Hill radius, of a planet is the region around it where its gravity dominates over the star's gravity. For a planet of mass m orbiting a star of mass m at distance r, the Hill radius is approximately r times m over 3m to the 1/3. For Earth orbiting the Sun, the Hill radius is about 1.5 million kilometers, or roughly 4 times the distance to the Moon. When two planets approach within a few Hill radii, strong gravitational interactions occur. The mathematics becomes complex. This is the famous three-body problem, 2 planets plus a star, which has no closed-form solution. But we can simulate it numerically. During a close encounter, one planet gains orbital energy while the other loses it. This isn't random. It's determined by the exact geometry of the encounter, the planet's masses, their approach speed, and angle. The planet that loses energy drops into a lower, tighter orbit. It moves closer to the star and orbits faster. The planet that gains energy moves to a higher orbit, farther from the star, slower orbital period. If the energy transfer is extreme enough, the planet that gains energy can have its total energy become zero or positive, E greater than 0. At this threshold, the planet has achieved escape velocity. It's no longer gravitationally bound to the star. Its kinetic energy equals or exceeds the gravitational binding energy. The planet follows a hyperbolic trajectory. It approaches the star, if it was scattered inward, swings around in a tight curve, then flies away forever, gradually slowing as it climbs out of the gravitational well, but never slowing to 0 velocity. It escapes. For a planet in Earth's orbit around the Sun, escape velocity is approximately 42 kilometers per second. Earth's actual orbital velocity is 30 kilometers per second, so it would need an additional 12 kilometers per second boost to escape, achievable in a close gravitational encounter with another planet. Once ejected, the planet's velocity relative to its former star gradually decreases as it climbs out of the gravitational well, approaching an asymptotic value called the hyperbolic excess velocity, the speed at which it will travel through interstellar space once it's far enough from the star that gravity becomes negligible. Typical hyperbolic excess velocities from planet-to-planet scattering range from 5 to 30 kilometers per second. Add the parent star's velocity through the galaxy, about 30 kilometers per second in random directions, and you get rogue planets moving at 20 to 50 kilometers per second in the galactic reference frame. This velocity range matches observations beautifully, confirming that gravitational scattering is the dominant ejection mechanism.
Not all planetary systems are equally prone to ejecting planets. The system's architecture, which planets exist at which orbital distances with which masses, determines stability. The Hill stability criterion. A simplified stability criterion comes from considering mutual Hill radii. For two planets to avoid close encounters indefinitely, they must be spaced far enough apart that their orbits don't cross even when eccentricities pump up due to perturbations. The critical spacing is approximately 10 mutual Hill radii. If two planets are closer than this, the system is likely unstable on timescales of millions to hundreds of millions of years. Our solar system barely satisfies this criterion. The spacing between Venus and Earth is about 10 mutual Hill radii. Earth and Mars are about 15 mutual Hill radii apart.
Jupiter and Saturn are well separated at about 25 mutual Hill radii. But many exoplanetary systems are more tightly packed. Systems with multiple hot Jupiters or with super-Earths in compact orbits often have spacings less than 10 mutual Hill radii. These systems are living on borrowed time. They might appear stable now, but over hundreds of millions of years, perturbations will accumulate, eccentricities will grow, and eventually close encounters will occur. Some planets will collide, others will be ejected. Mass hierarchy and dominance. Systems with one dominant massive planet, like Jupiter in our system, are more stable than systems with multiple comparable mass giants. Jupiter's mass is 318 Earth masses. Saturn is 95 Earth masses. The ratio is about 3.4 to 1. This mass hierarchy means Jupiter dominates the dynamics. When Jupiter and Saturn interact gravitationally, Jupiter's orbit changes little, while Saturn's changes more. Contrast this with a system having 3 planets, each of 100 Earth masses on relatively close orbits. No planet dominates. Gravitational interactions affect all 3 similarly. The system is chaotic, unpredictable, likely unstable. Computer simulations confirm this. Systems with 1 super Jupiter, 2 to 5 Jupiter masses, plus smaller planets are typically stable. Systems with 3 comparable mass Jupiters typically eject at least one within 100 million years. The role of resonances. Orbital resonances can stabilize or destabilize systems depending on circumstances. A mean motion resonance occurs when 2 planets' orbital periods have a ratio of small integers. The 2 to 1 resonance means one planet orbits twice while the other orbits once. The 3 to 2 resonance means 3 orbits versus 2. Near resonances, gravitational perturbations repeat at the same orbital phase each time, allowing small forces to accumulate. This can stabilize, if the resonance is exact and other conditions are right, as with many moon systems. The repetitive perturbations can lock the planets into stable configurations. Destabilize, if the system approaches but doesn't lock into resonance. The perturbations can pump up eccentricities and inclinations, leading to chaos and ejection. In our solar system, Jupiter and Saturn are currently near a 5 to 2 resonance. In the Nice model, they crossed through a 2 to 1 resonance about 600 million years after formation, triggering the late heavy bombardment and possible ejection of a 5th giant planet.
The scientific consensus on rogue planets has evolved from skepticism to acceptance to active investigation over the past 15 years. Key figures and their views. Dr. Takahiro Sumi, Osaka University, whose 2011 survey catalyzed the field, has stated, "Free-floating planets are at least as numerous as stars, possibly much more so. We're only seeing the tip of the iceberg, the Jupiter-mass ones. Smaller rogues could outnumber stars by 10 to 1 or more." Dr. Samantha Lawler of University of Regina, who specializes in N-body simulations of planetary dynamics, argues, planetary ejection is not an aberration, it's a fundamental outcome of formation physics. Nearly every multi-planet system likely ejects at least one world. The rogues we detect are the natural casualties of gravitational chaos. Dr. Sean Raymond of the University of Bordeaux, whose work on planetary formation has illuminated system architectures, notes, "For every exoplanet we see orbiting a star, there's probably at least one that was ejected during the system's violent youth. The galaxy is full of orphan worlds." Dr. David Bennett, NASA Goddard, principal investigator for Roman Space Telescope's microlensing survey, predicts, "Within a decade, we'll have a statistical census of rogues down to Mars mass. This will finally answer fundamental questions about planet formation that we can't answer by studying planetary systems alone, because we'll see what got ejected, not just what survived." Dr. Dorian Abbott of University of Chicago,
whose theoretical work demonstrated subsurface ocean viability, maintains rogue planets with thick hydrogen atmospheres could maintain liquid water for tens of billions of years, longer than any star will live. They're potentially the most stable habitats for life in the universe. Dr. Sarah Seeger of MIT, renowned exoplanet researcher, has written, "We've barely begun to explore the possibility of life on rogues. Our detection methods are still primitive, but given the sheer numbers, trillions of Earth-mass rogues, even a tiny fraction harboring life would mean billions of hidden biospheres." Philosophical implications. The discovery of rogues challenges fundamental concepts. What is a planet? The IAU defines a planet as an object that 1. Orbits the sun, or a star, 2. Has sufficient mass for self-gravity to achieve hydrostatic equilibrium, 3. Has cleared its orbital neighborhood. Rogues fail criterion number 1. Are they planets? Most astronomers say yes. Formation mechanism and intrinsic properties matter more than current orbital status. A rogue is a planet that was ejected, not a different type of object. But the debate reflects deeper questions about categorization and definition in astronomy. Planetary systems without stars. If a rogue has moons, and some probably do, is that a planetary system? A Jupiter-mass rogue with 4 large moons would functionally resemble the Jovian system, just without the sun. Some researchers propose planemo, planetary mass object, as a broader category encompassing planets orbiting stars, rogues, and sub-brown dwarfs. The ubiquity of planets. Rogues demonstrate that planets aren't rare, they're not special, they're a fundamental outcome of star formation. Every star probably forms planets, and many of those planets end up as rogues. The universe isn't mostly stars with occasional planets, it's mostly planets, with some orbiting stars and even more drifting free. This forces us to reconsider fundamental assumptions about planetary systems, cosmic architecture, and where to search for life in the universe.
The 2020s and 2030s will be a golden age for rogue planet discovery and characterization. Multiple missions and observatories are coming online specifically designed to detect and study these wandering worlds. Nancy Grace Roman Space Telescope, the microlensing revolution. Launching in May 2027, Roman represents the most significant advance in microlensing capability ever. The telescope's specifications are extraordinary for microlensing. 2.4-meter primary mirror, same as Hubble, wide field instrument with 300-megapixel camera, field of view 0.28 square degrees, 100 times larger than Hubble's WFC3 IR, pointing stability allowing continuous monitoring for months. The planned microlensing survey will monitor a 0.2 square degree field in the galactic bulge containing approximately 200 million stars. Observations will occur during bulge seasons, periods when the galactic bulge is visible from Roman's orbit, each year for at least 5 years, possibly extending to 10 years if the mission continues. Detection predictions vary, but estimates suggest 500 to 1,000 free-floating Jupiter-mass planets if SUMI's frequency estimates are correct. 2,000 to 5,000 if frequencies are higher, as some studies suggest. Hundreds of Earth-mass rogues detectable via the shortest events. Dozens of Mars-mass or smaller rogues in optimistic scenarios. Roman's sensitivity extends down to approximately 0.1 Earth masses, Mars-sized, for favorable events, brief brightenings lasting 30 to 60 minutes. Detecting these requires continuous monitoring, no gaps, high photometric precision, measuring brightness to 1% accuracy, and rapid data processing to identify events in real time. The mission will also search for rogues with moons. When a rogue with the moon lenses a background star, both bodies contribute to the lensing signal. The light curve shows additional features, small spikes or asymmetries that reveal the moon's presence.
Roman might detect dozens of rogue plus moon systems, providing the first statistical sample of satellite populations around free-floating planets. Vera C. Rubin Observatory, Time Domain All-Sky Surveys. The Rubin Observatory in Chile began operations in 2025 with its 8.4-meter mirror and 3.2 gigapixel camera, the largest digital camera ever built for astronomy. Surveys the entire visible sky every 3 nights, creating a time-lapse movie of the universe. While designed primarily for other science, asteroids, supernovae, dark matter mapping, it will contribute to rogue planet science in unexpected ways. Detecting nearby rogues via proper motion. Very close rogues, within a few light years, might be faintly detectable in Rubin's deep images. Over months to years, they'll show measurable motion against background stars, called proper motion. Rubin's repeated all-sky coverage will catch these moving objects. Occultations, extremely rare events where a rogue passes directly in front of a star, not close enough for microlensing, but close enough to block starlight, will cause brief disappearances. Rubin's time domain coverage might catch a few of these per year across the whole sky.
Serendipitous discoveries. The sheer volume of data, hundreds of terabytes of images each year, will contain unexpected finds. Unusual moving objects, anomalous brightening events, all flagged by automated software for human follow-up. Extremely large telescope, direct imaging of nearby rogues. The ELT, under construction in Chile's Atacama Desert, with completion expected in the late 2020s, will have a 39-meter segmented primary mirror, the largest optical infrared telescope ever built. Its contribution to rogue planet science will be direct imaging of the nearest rogues within 20 light-years. For young rogues, less than 100 million years old, still warm, resolved imaging showing the planet as a disk, not just a point. Multi-wavelength spectroscopy revealing atmospheric composition in detail. Time series photometry measuring rotation periods and detecting weather. Direct imaging of moons, if large enough and far enough from the planet. For old, cold rogues, detecting thermal emission from ancient rogues at 40 to 50 K, extremely challenging but potentially possible for the nearest ones. Studying how their atmospheres cool and condense over billions of years, searching for companions, brown dwarfs or stellar companions at wide separations. The ELT's adaptive optics system will correct atmospheric blurring in real time, achieving angular resolution approaching the theoretical diffraction limit, about 10 milliarcseconds in infrared wavelengths. This is sharp enough to resolve a planet at 10 light-years as a small disk rather than a point. James Webb Space Telescope, continuing survey programs. JWST's contribution to rogue planet science continues through the 2020s with multiple large survey programs. Star-forming region surveys, Orion Nebula, 1,350 light-years, hundreds of hours imaging and spectroscopy. Taurus Molecular Cloud, 450 light-years, survey of young stellar objects and free floaters. NGC 1333, 1,000 light-years, deep imaging searching for faint free-floating objects. Spectroscopic follow-up, detailed spectra of dozens of young rogues. Atmospheric composition, H2O, CH4, CO, CO2, NH3. Cloud properties, composition, altitude, coverage. Rotation rates and variability studies. Pushing detection limits, searching for cooler, older, fainter rogues than previously possible, attempting to detect objects down to 0.3 Jupiter masses in optimal cases, measuring the mass function, frequency versus mass, for young rogues in star-forming regions. Breakthrough starshot and interstellar probes. Looking further ahead, proposed interstellar probe missions could potentially encounter rogue planets en route to nearby star systems.
The Breakthrough Starshot Initiative proposes launching thousands of tiny spacecraft accelerated to 20% the speed of light using powerful laser arrays. At this speed, they'd reach Proxima Centauri in about 20 years. During the journey, these probes would traverse the volume between our Sun and Proxima Centauri. Statistical models suggest this volume contains dozens of rogue planets. If the probes had sufficient sensitivity and field of view, they might detect some of these rogues via their thermal emission or via occultation of background stars. Even more ambitious, NASA's interstellar probe concept proposes a spacecraft traveling at 5 to 7 AU per year, slower than Voyager but with better trajectory, reaching 1,000 AU from the Sun in about 50 years. Such a probe would traverse the outer solar system and inner Oort cloud, potentially detecting rogue planets passing through our neighborhood. These are long-term, speculative missions, decades away from reality, but they illustrate how detection techniques might evolve. Rogue planets fundamentally alter our understanding of how life might spread through the galaxy. Classical panspermia mechanisms. Panspermia, the hypothesis that life can transfer between worlds, comes in several forms. Lithopanspermia, rock-based transfer. Asteroid impacts on a life-bearing planet can blast rocks into space. If microorganisms are embedded in these rocks, protected from radiation and desiccation, they might survive the journey through space. If the rocks eventually fall onto another planet, the microorganisms could seed that world with life. This works on solar system scales. We found meteorites from Mars on Earth, proof that rock transfer between planets occurs. Some Mars meteorites appear to have experienced only mild heating during ejection and entry, suggesting microorganisms might survive the journey. But interstellar lithopanspermia seems much harder. Ejecting rocks at interstellar velocities, escape velocity from the Sun is 42 kilometers per second, requires extreme impacts. The rocks would be heated intensely, likely sterilizing them. Even if some microbes survived ejection, the journey through interstellar space takes millions of years. Long exposure to cosmic radiation would likely kill them. Rogue-mediated panspermia, a new mechanism. Rogue planets offer a completely different panspermia pathway. Step 1. A rogue planet with subsurface life drifts through the galaxy at 30 kilometers per second. Over 30 million years, it travels 100 light-years. Step 2. The rogue approaches a star system, say passing within 100 AU. As it enters the star's radiation field, its surface begins to warm slightly. Ice sublimates. Gases trapped in the ice are released. The rogue develops a temporary thin atmosphere. Step 3. Tectonic or volcanic activity, powered by tidal heating from moons or radioactive decay, might occur, especially as tidal forces from the star slightly stress the planet. Material from the subsurface ocean could be brought to the surface or ejected into space via geysers, volcanic eruptions, or impacts by interstellar debris. Some ejected material achieves escape velocity from the rogue. It enters orbit around the star. Over time, some fragments might impact planets in that system. If the fragments contain viable microorganisms from the rogue's subsurface ocean, the star system has been seeded with life. This mechanism has several advantages. Protection. Organisms are protected inside ice or rock during the journey, shielded from radiation. Long-term viability. Microorganisms can remain dormant in ice for millions of years. Experiments have revived bacteria from ancient ice cores. Galactic reach. Rogues travel vast distances. A single rogue might seed dozens of star systems over hundreds of millions of years. Reverse pathway. Rogues can also acquire life from star systems they pass near. If a rogue's gravitational influence triggers geological activity on a planet in that star system, or if an asteroid impact ejects material from that planet, some of that material might be gravitationally captured by the rogue, becoming embedded in its surface ice. The rogue then carries this biological sample to the next star system it encounters, millions of years later and hundreds of light years away. Implications for galactic biosphere connectivity. If rogue-mediated panspermia operates, then life in the galaxy is connected in ways we never imagined. Star systems separated by hundreds of light years with no direct contact might share common biological ancestry because a rogue planet passed through both systems, depositing samples from one to the other. The galaxy's biosphere wouldn't be isolated islands of life around individual stars. It would be a connected network, linked by wandering rogues carrying dormant microorganisms through the interstellar void. This has profound implications. Common biochemistry. If Earth life was seeded by panspermia from another star system, perhaps via a rogue, we might share common biochemistry with life elsewhere. DNA, RNA, amino acids, the genetic code. These might be galactic standards, not independent inventions. Rapid colonization. Life could spread through the galaxy much faster than previously thought. Instead of requiring deliberate interstellar travel by technological civilizations, life spreads naturally via rogues over hundreds of millions of years. Hidden diversity. Rogue planets themselves might host the oldest, most diverse biospheres. If life originated on a rogue billions of years ago, or was deposited there by panspermia from elsewhere, that rogue has potentially 10 billion years of continuous evolution, longer than Earth has existed. Rogue biospheres might contain organisms adapted to extreme conditions that would seem impossible to Earth-based life. Organisms that metabolize at near-freezing temperatures, organisms that can survive in ice for millions of years in dormant states, organisms with completely novel biochemistry. We might have much to learn from studying life on rogues if we can find it and access it.
What is the ultimate destiny of rogue planets across cosmic timescales? Short-term fate, next few billion years. Most rogues will continue wandering the galaxy for billions of years, following complex orbits around the galactic center. Some will have close encounters with stars. Probabilities are low, perhaps 1 in a million per billion years, but given vast numbers of rogues, thousands of encounters occurred galaxy-wide every year. Outcomes of stellar encounters. Capture. If geometry and velocities are right, the star can gravitationally capture the rogue, which becomes an exoplanet with an extremely eccentric orbit. Over time, tidal forces and gas drag, if the star has a planetary disk, might circularize the orbit. Disruption. If the rogue passes too close, within a few stellar radii, tidal forces can disrupt it, tearing the planet apart and creating a debris disk around the star. Scattering. Most encounters result in scattering. The rogue's trajectory changes, velocity shifts, but it remains free-floating. Some rogues will collide with other rogues, gas clouds, or debris in the interstellar medium. Collision probabilities are extremely low for planet-sized objects in the vast emptiness of space, but over billions of years, a small fraction will merge, shatter, or accrete material from molecular clouds. Long-term fate, 100 billion to 1 trillion years. Over these timescales, galactic evolution becomes important. Galactic mergers. The Milky Way will merge with Andromeda in about 4 billion years. This merger will gravitationally stir the stellar and planetary populations. Some rogues will be ejected into intergalactic space. Others will be scattered into different orbits. Stellar evolution. Stars die.
Over 100 billion years, most stars will exhaust their fuel. Red dwarfs, the most common stars, will continue shining, but sun-like stars and larger will become white dwarfs, neutron stars, or black holes. Galactic evaporation. Over 10 to the 19 years, 10 billion years, gravitational encounters will gradually eject most stars and planets from the galaxy. The galaxy evaporates, leaving behind a central massive black hole and a sparse halo of wandering stars and rogues. Rogues ejected from the galaxy become intergalactic wanderers, drifting through the cosmic voids between galaxy clusters at velocities too low to ever reach another galaxy before the universe ages beyond recognition. Ultra-long-term fate, beyond 10 to the 100 years. If current physics is correct, even planets eventually decay. Proton decay, speculative, some grand unified theories predict protons decay with half-lives around 10 to the 34 years. If true, matter is not stable on ultra-long timescales. Planets would gradually dissolve as their constituent protons decay. Black hole evaporation. Even black holes aren't eternal. Hawking radiation causes them to lose mass over time, eventually evaporating completely in 10 to the 100 years for stellar mass black holes. Heat death. The universe continues expanding and cooling. Eventually, all stars burn out, all black holes evaporate, and the universe reaches maximum entropy, a state of maximum disorder where no free energy remains to drive any processes. In this far future, rogue planets, if they still exist, will be isolated relics drifting through expanding voids, cooled to temperatures approaching absolute zero, with no stars, no light, no energy sources, except infinitesimally slow quantum vacuum fluctuations. But before that happens, across the next few billion years, rogues will continue their journeys, silent witnesses to galactic evolution, carrying with them possibly ancient biospheres, drifting through the cosmic dark. The most profound implications emerge when we consider that the universe contains more planets drifting in darkness than orbiting stars in light. That life might exist in forms and places we never anticipated, that our search for cosmic companions has barely begun to explore the true diversity of worlds in the cosmos.
One of the most unsettling questions about rogue planets: could one pass through our solar system? What would happen if it did? Statistical probability. Let's calculate the likelihood using population estimates and orbital mechanics. If there are 2 Earth mass rogues per star, and stars in our neighborhood have average spacing of about 5 light-years, then the density is 2 rogues divided by 5 light-years cubed, approximately 0.016 rogues per cubic light-year. Our solar system has a radius of about 100,000 AU, or 1.5 light-years, if we include the Oort cloud. The volume is approximately 4/3 pi times 1.5 cubed, or 14 cubic light-years. Expected number of rogues in this volume, 0.016 times 14, approximately 0.22. So at any given time, there's roughly a 20% chance a rogue exists somewhere within the Oort cloud volume. But existing in the same volume doesn't mean on a collision course. The rogue would need to pass through the inner solar system, within, say, 100 AU, to pose any threat. The cross-sectional area of the inner solar system, about 100 AU radius, is tiny compared to the Oort cloud volume. A rogue drifting through the Oort cloud has only about a 0.001% chance of passing through the inner 100 AU.
So the probability of a rogue currently existing in the Oort cloud and being on a trajectory toward the inner system is roughly 0.2 times 0.00001 equals 0.00002, or 0.002%. At any given moment, the probability is negligible. But rogues are moving. At 30 kilometers per second, a rogue crosses 1 light-year every 10,000 years. Over millions of years, many rogues will pass through our neighborhood. Over the next billion years, approximately 100,000 rogues will pass within 1.5 light-years of the Sun. Of those, perhaps 1 to 2 will pass within 100 AU of the Sun. Over 4.6 billion years, the age of the solar system, perhaps 4 to 10 rogues have passed within 100 AU. Gravitational effects. If a rogue does pass through the inner solar system, what happens? It depends critically on the rogue's mass and closest approach distance. Jupiter mass rogue passing at 50 AU, roughly Pluto's distance, minimal effect on the inner planets, Earth, Mars, Venus, Mercury. Possible perturbations to outer planets, Neptune and Uranus. Scattering of Kuiper belt objects and Oort cloud comets, potentially sending some toward the inner system, increasing comet impact rates for a few million years. Jupiter mass rogue passing at 10 AU, significant perturbations to outer planets, possible destabilization of asteroid belt. Small perturbations to inner planets, changing orbits by fractions of a percent, enough to slightly alter Earth's climate over millions of years, but not enough to immediately threaten life. Jupiter mass rogue passing at 5 AU, Jupiter's current orbit, major disruption to outer solar system, possible ejection of one or more outer planets, significant perturbations to inner planets. Earth's orbit could change by several percent, potentially moving Earth too close to the Sun, a runaway greenhouse, or too far, a snowball Earth. A super-Jupiter, 3 to 5 Jupiter masses, passing at 1 AU, catastrophic disruption. Inner planets scattered or ejected. Earth would almost certainly be ejected or have its orbit so dramatically altered as to become uninhabitable. Solar system architecture completely rearranged. The good news, close passages are extremely rare. The probability of a Jupiter mass rogue passing within 5 AU in the next billion years is perhaps 0.01%, 1 in 10,000. Within 1 AU is even less likely, perhaps 1 in a million. We're probably safe, but probably isn't certainly. Detection and warning time. Could we detect an approaching rogue planet in time to prepare, or at least know what's coming? For a typical rogue at 30 Kelvin, detection is extremely difficult. It emits negligible infrared radiation. It reflects almost no light. There's no nearby star to reflect. It's essentially invisible until it's very close. The best detection method might be gravitational perturbations. If a massive rogue approaches the outer solar system, its gravity would slightly perturb the orbits of known objects, like comets, the Kuiper belt objects, and even outer planets. Careful astrometric measurements might detect these perturbations months or years before the rogue reaches the inner system. But subtle perturbations are hard to distinguish from normal orbital variations. We might not recognize the signal until the rogue is already here. More optimistically, future all-sky infrared surveys might detect nearby rogues before they enter the solar system. The Roman Space Telescope and others will catalog millions of faint infrared sources. A rogue at 5 light-years might be faintly detectable. Tracking its motion over years would reveal its trajectory, allowing us to predict if it will pass through our system. Warning time could be decades to centuries, enough time to plan, though what we'd actually do is unclear. We can't deflect planet-sized objects. We can't alter their orbits. We can only watch and hope the passage isn't too close.
Beyond the science, rogue planets force us to confront profound philosophical questions about existence, isolation, and the nature of cosmic homes. The meaning of home in a nomadic universe. For all of human history, home has meant a place, a location we return to, where we belong, where we're rooted. For planets, home has always meant a star system. Planets belong to stars. They orbit, they're warmed, they're defined by their stellar relationship. Rogues challenge this. A rogue planet has no home. It's perpetually displaced, an exile wandering without destination or anchor. Yet the rogue is also completely free. It's not bound by a star's gravity. It can travel anywhere, cross the entire galaxy, experience regions of space no orbiting planet will ever see. Is this freedom or loneliness, adventure or punishment? The answer depends on perspective and perhaps on whether anyone lives there. Life without light, a thought experiment. Imagine you're an intelligent being that evolved on a rogue planet. You live in a subsurface ocean, kilometers below the ice. Your entire world is this ocean, the rocky floor below, the ice ceiling above, the hydrothermal vents that provide warmth and chemical energy. You've never seen light. Your species has no concept of vision because there's nothing to see. You navigate by sound, touch, chemical sensing. Your science is sophisticated. You understand chemistry, thermodynamics, perhaps even quantum mechanics. But you've never developed astronomy. How could you? There are no stars to observe, no celestial bodies to track, no sky to wonder about. Your cosmology might be completely different from ours. You might think the ocean is all that exists, or you might theorize that your world is embedded in some larger structure, but have no way to test the hypothesis. Then, one day, your civilization develops the technology to drill through the ice. You send a probe to the surface. It emerges into a frozen wasteland at 30 Kelvin. Instruments detect faint electromagnetic radiation, light, a phenomenon you've never encountered. The probe looks up and sees stars, thousands of them, pinpoints of light in absolute darkness. This discovery would shatter your worldview. You'd learn, 1, your ocean is not the universe, it's a tiny speck. 2, there exist vast, incomprehensible regions beyond your world. 3, other objects, stars, exist, separated by distances so vast it takes light years to cross. And 4, your world is traveling through this larger universe, though you can't feel the motion. The psychological impact would be staggering. Everything you thought you knew about existence would need revision. Philosophers, theologians, scientists would struggle to integrate this new reality. We humans experienced something similar when Copernicus showed Earth isn't the center of the universe, when Hubble showed galaxies extend beyond the Milky Way, when we learned the universe is 13.8 billion years old and contains hundreds of billions of galaxies. But for a rogue civilization, the discovery would be even more shocking because they'd have no preparation, no gradual realization. They'd go from thinking their ocean is everything to discovering an infinite cosmos in one revelation. The question of contact. If billions of rogue planets exist, and even a tiny fraction harbor life, and even a smaller fraction harbor intelligent life, then statistically, there might be dozens to hundreds of technological civilizations on rogue planets in the Milky Way right now. We'll probably never detect them. They emit no radio signals. Why would they? There's no one to talk to. They don't modify stars. They don't have stars. They leave no obvious technological signatures. They're invisible, silent, isolated. Could such civilizations develop space travel? Possibly. They could launch probes to the surface, establish surface bases, even launch interstellar missions, though without stars to navigate by, such missions would be challenging. But they would have no obvious reason to advertise their presence. They're not looking for other civilizations because they don't know other civilizations are possible. Their universe is the ocean, the ice, the rocky core. Why would they search for something they can't imagine? The universe might contain thousands of intelligent species we'll never contact, not because they're too far away or technologically primitive, but because they exist in a context so different from ours that communication is impossible. Our place in a rogue-dominated universe. If billions of rogue planets outnumber orbiting planets 10 to 1, then Earth is unusual. We're the minority. Most worlds drift in darkness. This inverts our cosmic perspective. We think of Earth as a fragile oasis in a hostile universe, but maybe we're the lucky ones. We have a star, we have light, we have warmth that doesn't require kilometers of ice and radioactive decay. Rogues are the norm. We're the exception. This should humble us. The universe doesn't care about sunlight or stars or the conditions we consider habitable. Life finds a way in darkness, in cold, in isolation. The cosmos is stranger, more diverse, more filled with possibilities than our light-bound perspective allows us to imagine. The final question: are we alone? Probably not. With trillions of planets, orbiting and rogue, the numbers favor life existing elsewhere. But are we alone in our ability to see the universe? Quite possibly. We might be among the few civilizations, blessed or cursed, with stars to observe, skies to wonder about, cosmic context to contemplate. Most intelligent beings might live in darkness, aware only of their immediate environment, never knowing the universe extends beyond their ocean walls. We can see the cosmos. We can measure it, map it, understand it. That's an extraordinary privilege, one we should not take for granted.